students. Now let's continue the arithmetic function. Okay, so let's see one theorem first. Theorem: if n greater than 1 be any integer, then d of n is equal to product of p raised to alpha divides n, product of alpha plus 1, where p raised to alpha divides n. So proof of this, let's see the proof. Let n greater than 1 be any integer, then canonical form of n is n equal to p1 raised to alpha 1, p2 raised to alpha 2, so on up to pr raised to alpha r, where p1, p2, so on up to pr are distinct primes, then all positive divisors n are of the form m equal to p1 raised to beta 1, p2 raised to beta 2, and so on up to pr raised to beta r, where 0 less equal beta I less equal what? Alpha I, where I goes from 1 to so on up to what? R. This is for all I. Okay. Now here this is a remark, you know this. We had used this in previous video for solving for finding the positive divisors of a number, any integer, a big integer which we cannot find out orally, or also for small integers also. Then there are alpha 1 plus 1 choices of beta 1. Then alpha 2 plus 1 choices of beta 2. Okay, and so on. Alpha r plus 1 choices of beta r. Okay, that is there are alpha 1 plus 1, alpha 2 plus 1, and so on up to alpha r plus 1 times choices of m. Here alpha 1 plus 1 choices of beta 1. For beta 1 we have these many choices. Alpha 2 plus 1 choices of beta 2, and so on. So for m, the product of these times choices of m, that is divisors of n. The choices are nothing but the divisors of n. While solving the previous example of 180, while taking beta 1 we got 6 divisors there. Again for beta 2 we get 6 as such. So these are what? Divisors. Therefore d of n is nothing but this product, alpha 1 plus 1, alpha 2 plus 1, and so on up to what? Alpha r plus 1, and therefore d of n is what? The product of alpha plus 1, where p raised to alpha divides on n. Now let's see example on this so that it will be clear to you. Example, let n equal to what? 50. Already we had taken it. So here n equal to 50, and that is equal to 2 raised to 1 into 5 square. Therefore alpha 1 is equal to 1 and alpha 2 is equal to how much? 2. Therefore d of 50 is how much? 1 plus 1 into 2 plus 1. So it will be 2 into 3. So that is 6. Again another example, suppose let n equal to 180. So for 180, here 180 can be written as 2 square into 3 square into what? 5 raised to 1. Therefore alpha 1 is equal to 2, alpha 2 is equal to 3 and alpha 3 is equal to what? 1. Why alpha 1 plus 1 choices are there or alpha plus 1 choices for each prime? Because we are counting from 0 to that number. So 0 to 2, so we get 3 different numbers for each alpha I there. Remember this thing. Therefore d of 180 will be what? This 2 plus 1, 3 plus 1 according to theorem, and 1 plus 1. So it will be 3 into 4, sorry 3 is not here, here also 2, so 3 into 3 into what? 2. So 9 to the how much? 18. Fine. Then let's take the next one. Another example, let n equal to 5438. So here 5438 equal to 2 into 2719, 2 raised to 1 and this also raised to 1. Therefore alpha 1 is equal to 1 and alpha 2 is equal to what? 1. Therefore d of 5438 is equal to 1 plus 1 into 1 plus 1, that is 2 into 2, so it will be how much? 4. Fine. Now let's take one corollary on that theorem. So let me take one corollary on that theorem of this corollary. If m and n are relatively prime, then d of mn equal to d of m into d of n. Proof of this, let m equal to p1 raised to alpha 1, p2 raised to alpha 2 and so on up to pr raised to alpha r, and n equal to q1 raised to beta 1, q2 raised to beta 2 and so on up to qk raised to beta k. Okay. Since m and n are relatively prime, the prime pi's are distinct from what? Qj. Obviously if these are relatively prime, so the prime factorizations are different. So therefore what is m into n? M into n is p1 raised to alpha 1, p2 raised to alpha 2 and so on up to pr raised to alpha r, and q1 raised to beta 1, q2 raised to beta 2 and so on up to qk raised to beta k. Okay. So From that, what is d of mn? D of mn is alpha 1 plus 1, alpha 2 plus 1 using that theorem, so on up to what? Alpha r plus 1 into beta 1 plus 1, beta 2 plus 1 and so on up to what? Beta k plus 1. So this is nothing but d of m, and this remaining part is nothing but d of n. So as such we get d of mn is equal to d of m into d of n. Okay. Now let's see from this, let's see one definition. That definition is of multiplicative function. Multiplicative function. An arithmetic function, an arithmetic function f is said to be multiplicative, if f of mn is equal to f of m into f of n, wherever m and n are relatively prime. So for example, look at here, this d of n, look at here, this one is the corollary, is an example for that. Also phi of n are multiplicative functions, but this omega n is not multiplicative function, because for example n equal to 50, that will be 2 into 25. So and omega of 50 is equal to how much? 2. But what about omega of 2 into omega of what? 25. So omega of 2 is what? 1, and omega of 25 is also what? 1, because 25 is nothing but 5 square. So its value is also 1. Now here omega 50 and this product are not same. Here omega 50 is not equal to omega 2 into omega of what? 25. These are not same, or means it is not a multiplicative function. Now let's see the remark. Let m equal to m1 m2, where m1 and m2 are relatively prime, then d divides m if and only if d equal to d1 d2, where d1 divides m1 and d2 divides m2, and d1 d2 are what? Relatively prime. d1 d2 are relatively prime. So d divides m, then d can be written as d1 d2, then that d1 divides m1 and d2 also divides what? m2, if these are what? Relatively. Fine. Now another remark. If f is multiplicative, multiplicative, then f of 1 is equal to 1. To check this, if n and 1 are relatively prime for all n belongs to what? Z plus. Therefore, f of n into 1 is equal to f of n into f of 1. That is, f of n is equal to f of n into f of 1. That gives f of 1 is equal to what? 1. Comparing both sides, we get f of 1 is 1. Now, let's see one theorem that is an important theorem here. It is on multiplicative function. Okay. So, theorem. It is an important theorem. If f is multiplicative function, f is multiplicative function and f of n is equal to summation f of d divides what? N. For all n belongs to what? Z plus. Then f of n is also multiplicative. Proof of this. Given that f is multiplicative function, f is multiplicative function, that is, if m1, m2 are relatively prime, then f of m1, m2 is equal to f of m1 into f of m2. Call it as equation number 1. Okay. Now claim. What is our claim? F of m1, m2. Capital F of m1, m2 will be what? F of m1 into f of m2. That thing we have to show. For small m1, for small f it is given to us, and relation between capital F and small f is this given to us. Fine. So now as fn is equal to summation f of d divides n. Therefore, capital F of m1, m2 is equal to summation f of d divides what? m1, m2. D divides m1, m2. Now just we have seen it. It can be written as summation f of d1, d2. Okay, where d1 divides m1 and d2 divides m2. We had written a remark just before that. Fine. Now, because, why does this we can write? Because if m1 and m2 are relatively prime, we can write this. And d divides m1, m2, then d is uniquely written as a product of a divisors d1 of m1 and a divisor d2 of m2, and d1, d2 are what? Relatively. Therefore, f of d1 d2 is equal to f of d1 into f of d2. So this gives capital Fn is equal to summation d1 divides m1 into f of d1 and summation f of d2 divides what? m2. It can be written as due to this. So therefore we get f of m1 m2 is equal to, this is f of m1 and this is f of m2. So what can we say? F is multiplicative function. So this says f is multiplicative. F is multiplicative function. F is multiplicative function. Now let's see corollaries on this. Corollary. One, for any positive integer, n in d of n is multiplicative. D of n is multiplicative. So proof. By definition, d of n is equal to summation 1 d divides what? n. If f of n is equal to 1 for all n belongs to what? Z plus, then clearly f is multiplicative. F is multiplicative. And d of n equal to summation f of d divides what? n. So this gives d of n is multiplicative. D of n is what? Multiplicative. Now corollary 2. For any positive integer n, d of n is product of alpha plus 1 where p raised to alpha divides on n. So proof, as d of n is multiplicative function, if n equal to product p raised to alpha where p raised to alpha divides n, that is equal to p1 raised to alpha 1, p2 raised to alpha 2 and so on up to pr raised to what? Alpha r. Then d of n will be d of this product p raised to alpha where p raised to alpha divides on n. So that is same as product of dp raised to alpha where p raised to alpha divides n. But the divisors of p raised to alpha are what? 1, p square and so on up to what? P raised to alpha. Therefore, d of n, what it is? This is number of divisors. How many are they? Alpha plus 1. So product of whom? Alpha plus 1, where p raised to alpha divides what? N. This is a proof of this corollary. Now, here we will stop. In next video, we will see some examples and some theorem on this. Okay. Thank you.